Welcome to lecture 11 of MCS 472 on industrial mathematics and computation. So today we close off a chapter on the Fourier transform, on the discrete Fourier transform, with the outline of two applications of the fast Fourier transform. So to recap, where are we? So this is the main picture also behind me on the board. This lecture treats the Fourier transform, the discrete Fourier transform, as a black box. What we need to remember mostly of the discrete Fourier transform is that it allows us to turn a convolution into a component-wise product. So if we need to compute a convolution, then we may as well take the inverse discrete Fourier transform on the component-wise product of the Fourier transforms of the two inputs. That is what the slide says. In some sense, it's a nice property, but that property alone doesn't buy us anything. But then there is the fast Fourier transform. So the fast Fourier transform that does this in n log n time. So we encounter the fast Fourier transform when we want to compute the output of a filter. So we've seen that linear time invariant causal filters are entirely determined by their impulse response. So the coefficients of the impulse response are here denoted by the little h. So the big H is the transfer function. So if we want to compute the output given an input u and the impulse response h, then we have to do a convolution. Now, if we do the Fourier transform, the fast Fourier transform on the input and on the impulse response, then the inverse fast Fourier transform on the component-wise multiplication, so that means the first component of u with the first component of h, second component of u times the second component of h. Very regular. Then if we do this inverse Fourier transform on the component-wise product, then we have the output of our filter. Here is the computational importance. So our course is mainly computational. So we have the n log n of the fast Fourier transform and also of the inverse fast Fourier transform. So the main point is that the n square operation is reduced to a linear operation where the cost is linear, not quadratic, plus a number of times an n log n operation. But n log n is also quasi-linear. Okay, so that is the computational setup, at least in theory. How is this now applied? So with the fast Fourier transform, we can actually do the online filtering. So what does that mean is that we can compute the spectrum of a signal, then do the corrections in this frequency domain, and then transform back into the time domain. We will distinguish between low-pass filters, filters that remove the highest and the middle frequencies. Then there is the high-pass filter where only the high frequencies are passing. And then there is the in-between, the band pass, where we can set only certain frequencies to pass. That's the concept. So how do we now actually do this? We have the FFT package that wraps the FFTW software. So the name of the package is the same of the software, FFTW. The W stands for the West. So here is the here are the instructions for two plots. So where we construct a signal that is the sum of two sine functions. One sine function runs at frequency 4, so the 4 here is important, and the amplitude 3. The other signal runs at a lower frequency, but at a much higher amplitude, at amplitude 5. So in the time domain, we are going to see big wobbles and small wobbles. That may be an indication that there is some composition going on, so it's not a pure sine function. The nature of the signal will actually become very clear when we go to the frequency domain, when we make the spectral plot. So the instructions are also here. The main important step here is the FFT of the time samples. So we start with continuous functions, but what we actually are doing, we have periodic data that we feed as input to the for the fast Fourier transform. So we look at the amplitudes then. So the outcome of the fast Fourier transform is a sequence of complex numbers. We take the absolute values and we scale. So remember the normalization in the Fourier transforms. Then we make the sequences of the frequencies, and we plot the frequencies and the first amplitudes. So the first 80 data we essentially plot. We divide by 4 because our time interval is going from 0 to 4. So this is why our x-sticks go from 0 to 20. So now we have two plots. So the first plot is in the time domain. We see the amplitude. So we had an amplitude 3 and 5. So we could make at most 3 plus 5 is 8, but we don't really get there because of the differences in the frequencies. So we have the big wobbles and the small wobbles. Okay, so then we see the spectrum of the signal. So what we see is that we see two spikes. One spike has height 5 at position 2. So that means that we have an amplitude 2 signal running at frequency 5, and then we have an amplitude I think I mislabeled this here. So we have the frequency amplitude. So I switched the axis, so I will still fix this. So the amplitudes are 3 and 5, so they are the vertical axis. So this should be amplitude. Here we have a frequency. So this is the spectral plot. Alright, so we did a spectral analysis. What good is this now? Well, let's add some low amplitude noise. So to the original signal, we add some normal vectors. So sometimes it will be less, sometimes it will be plus. So the normally distributed numbers give us an average mean of 1. We scale that down, we multiply by 0.3. And we make the same plot. So to the plotting instructions, we add the plot of the noisy signal. Okay, so here is the time amplitude plot. So the original signal is in blue. You see somewhere the blue still sticking out, but you can see the low amplitude noise, which occurs at all frequencies. So that's why at the peaks and the valleys, we see that there is most change in the because of the noise. Okay, so then we make the spectral plot again, and the axes are wrongly labeled. So the horizontal axis are the frequencies. So we still see the two spikes. And if we are really careful, we see that one of the spikes is a little bit lower. So that happens. But then we see all these wobbles. So they are the amplitudes. So the vertical axis here are the amplitudes. You see the low amplitude noise happens everywhere. But you see, for the remainder, so for the filtering purposes, we can actually get rid of all the low amplitude stuff by simply taking the output of the FFT and setting all values below a certain threshold to 0. That's what the amplitude filtering does. Here it is. So we want the sequence of the same length. Julia also has the filter construction, but that will create a shorter vector. And that's actually not what we want. We simply want to, so here we want to vector an array of the same length. So we have our output of the FFT, the capital F, and we multiply every number by 0 or 1. It will be a 1 if the absolute value of the number is larger than 50. So the 50 seems very arbitrary, and I looked at the numbers. So here I spared you the numbers. The Jupyter notebooks are posted, and you're more than welcome to look at these Jupyter notebooks. So you can look at the numbers of the Fourier transform, and you see that there are indeed, you can notice the spikes. And then by well-chosen constant 50, we actually remove all the low amplitudes. Note that this filtering is just one line. So the output of the test gives me true or false, and that gets converted to the integer 1 or 0. So the numbers that are large enough, they survive. The other ones are multiplied by 0. Okay, so that is our filtering, and here you see the filtered spectrum. Again, I have to emphasize this is the amplitude, the vertical axis, and the frequencies are the horizontal axis. Okay, we have filtered. So I've showed you also last time already the FFT. What is the inverse? Well, it is IFFT. So the only thing that we need to do now is we need to make sure that we get the real parts only. So the plot of the after the IFFT is just selecting the real numbers from the inverse output. And that is it. Here we have the corrected signal. Now you have to take my word for this, because it looks just like the original signal. Now you may notice, well, you may not notice this if you look at only this slide, but you may notice that the peaks may be a bit lower, and the valleys may be a little bit higher. So the amplitude of the corrected signal may be a little bit shifted as well, because that was because of these peaks. The peak at the lower frequency, at the highest frequency, the lowest peak was a bit lower. But other than that, the shape looks great. And we have again two sine functions. So this is the amplitude filtering. I mentioned the low pass, high pass, and band pass filtering. There it's actually easier. You have to take the Fourier transform, and the Fourier transform of the signal will show you the peaks at these frequencies. What then you have to do, if you want a high pass filter, you have to set all the lowest frequencies to 0, lower than the threshold. So the exercise here invites you to play with this. If you can build one of the filters, then you know how to do the other two types as well. But we will make a signal with three different frequencies, one low, one middle, one high, and then with the filters, low pass, high pass, band pass, we can filter the frequencies. If you want to do this more as a programming exercise, you can encapsulate your filters as Julia functions. That is fine, but not strictly necessary. Okay, this is our first application to filtering. Filtering that is online, that can be done online because of this quasi-linear costs. Okay, so let us now look at another application of the Fast Fourier Transform in the blurring and deblurring of images. So here is a familiar image. I think I captured this off one of the UIC websites. So we have the Chicago skyline behind three of our newest buildings. So this is our image that we can load with the images package. So the images package is a large meta package. It's when you are installing it, you will see that it will also install various other packages. So for our purposes, it is fine to start like that. So we will be using images, and here I called the name of the file building sky, and the extension is PNG, so it's a portable image format. I have done this in a Jupyter notebook that was started in a Jupyter session in the current folder. I could just work with the name of the file, and I will post also that picture. It may be that instead of just giving the string name, you may have to give the entire path name, or if you have downloaded the image somewhere else on your computer, you have to provide the entire full name of the path that leads to that file. So okay, so there is some hurdle here. So using images will install a lot of packages. Sometimes you may need to be patient. You need to have the image that you want to work with in the correct position. Also, the first time that I tried this was with a JPG file, and then it really didn't work as I hoped. So I had to use the converted image. Okay, but after that we have the numbers in our session. So if you look then at size of A, you see that it is a two-dimensional structure with 570 rows and 855 columns here. Okay, so let's see what we can do with this. We know we can slice an array, or a matrix. I can take the middle. So I take the middle of the rows, the middle of the columns, and here I had to not only convert to an integer but also round. So the odd number turned into a 0.5, and that gave a problem. So the middle, so I take 20 pixels to the left, 20 pixels to the right, 20 pixels up and down. So here you see kind of a very grainy image of the middle buildings, closest actually to more closer to UIC in the skyline. Okay, so this just to say that this allows us to be, we have the matrix operations at our disposal. But we cannot really compute with them all the way directly. If we look at the first element, so look at the type, then we see RGB. And actually also if you would select this, the image will show up. So the representation of the matrix or a slice is the rendering of the images because of the type of A. So what does RGB mean? It's one of the conventions to store images. So we have the primary colors, red, green, and blue, and all kinds of colors are combinations of these three primary colors. You see here that dump is interesting. Dump shows the content of a Julia variable. So here we have not only the type, but we also have the fields R, G, and B. The name of the type. So essentially they are unsigned 8-bit integers. So that's what they are. And we can convert them to floats if we want to compute with them. And why would we want to compute with them? Well, here is a useful operation. If we average the intensities, then we get to a grayscale picture. So this averaging operation here, notice the typing. So the AR, AG, AB, the red, green, and blue intensities are these unsigned integers. I convert them to 32-bit floats and then add them up. I can do that and divide them by 3. But then I want again to convert them to RGB codes. And here for the RGB codes, I can say that I want to use 30-bit floats. So this is what is called a pixel by pixel operation. So this is not a course on image processing or graphics processing, but graphics cards can do this extremely kind of one instruction, since the graphics cards have so many cores. One core can take care of one pixel, so to speak, almost. Okay, what are we using this for? Well, we're going to convert the color image to a grayscale image. So this is essentially a 32-bit floating point matrix, but where we store the elements in the RGB coding. So we have now a matrix of RGB floats, where every element is replaced by the average of the color intensities. So this operation is useful if we have a numerical matrix and we want to construct a color image or reconstruct a grayscale image. So we will use that also. So here, this looks back like in the 60s. So this is our grayscale image of the skyline. Okay, why do we do this? Well, then we have one single floating point matrix to work with. If you still want to work with the colors, you could work with three different matrices. So for each intensity, you use a separate matrix, and then you do everything three times over. By the way, when I installed the images, the package quaternions also was installed. There is a way to work with RGB numbers more directly when working with the quaternions. So in some sense, this we are in the FFT world where everything is naturally complex, but there is also the extension to the complex numbers, the quaternions. Now, a lot of what we are doing here could be the potential exploration for future projects. If you want to explore how quaternions are also extremely useful to practical applications, then this could be a way to a computer project or to a next project. Okay, so here we turn the matrix of grayscales, our A gray matrix, into a matrix C. So all the intensities are the same, so I'm just copying the red intensity. Speaking of intensities, so elsewhere the grass is always greener, so you can make your images greener, and so this is an exercise on computing with pictures. It's another picture, another in pixel by pixel processing. Take the familiar image or any other image that you want, preferably with grass in it, or some type of green, and make it somehow greener. This could be by just multiplying all the green intensities by a factor 1.1. But you could also do this simultaneously by lowering. So the intensities, it could be that they have to sum up by 1. So it may very well be that if you make the intensity of 1 raised in one intensity, also you have to lower the other intensities. Check that out in the RGB type if everything signs up to 1. And this is most likely also what we exploited in the grayscales. We were averaging the sum of the numbers, or perhaps not. Okay, now our actual application. So what is it that we want to do? So we still haven't used the fast Fourier transform. So with image processing, a lot of computations are pixel by pixel, or sometimes averaging. So later in this course, we will see models of diffusion, the way heat dissipates. So we ended our numerical analysis class, MCS 471, with a model of heat. That model can be used also for the fading out of images, where we kind of average all the pixels. So that could be another pixel by pixel operation, or where actually we start to use already the information of neighboring pixels. Okay, so here we are going to do a very expensive operation. So I will say it. So the bottom line here is that, well, what is the problem actually? We want to send out sensitive images. We do not want that anybody who intercepts our transmission would be able to see our sensitive images. So we will start to blur the images. And here is how we can do this. We can take a random matrix or any very special matrix, but for our purposes, I will use a random matrix. We will compute the image. So here if the x is an m by m m by n, so m rows, n columns. So then B, the blur matrix, has to be m by n. So and here the inverse is then here m to the power 3. So to blur, we do a matrix multiplication. To deblur, we also need to take the inverse. So perhaps we may take an orthogonal matrix. That will save us the inverse operation. So that's just then a transpose. But nevertheless, it's costly. So we were already happy when we didn't have to do the quadratic cost with the convolution, but now we are faced with a cubic cost. So if you have to make the transmission safe, I mean, sensitive images, you can think of streaming a video, and you do not want that non-paying non people who don't pay, who don't have the decoder or encoders. So there are also commercial applications here. So you do not want that your safe transmission slows everything down. Okay, so that's our motivation for the FFT. So can we have a two-dimensional Fourier transform? And the answer is yes, of course we can. So here is the definition. We have m rows and n columns. So we can take two primitive roots, the m primitive root so this is the subscript m, so this is the primitive root for the rows. And then we have the primitive root for the columns. Okay, so then we can define the discrete Fourier transform as a double sum, where we have the innermost sum running over the columns, so that's the first sum here. Then we use the primitive root with the column dimension, the omega n, and the outer loop then runs over the other primitive root, or we can flip things around. So this is how you store your matrices, row-wise or column-wise. They are the same because of the distributive properties of the addition with the multiplication. So this, by the way, could have been a nice exercise. Verify the properties of the discrete Fourier transform. By the way, I forgot to mention, if you ever wondered what's the intuition for going from the time domain to the frequency domain, we are making a lot of sums here, and sums may remind you of integration. So there is a continuous Fourier transform which is expressed as an integral. So you can integrate with respect to the time variable. That makes the time variable disappear. So we may come back to continuous transforms later in the course. Okay, here is an exploration. So this is an exercise, but could also more turn into a project. So the world of image processing is extremely extensive. Certainly if you're going to turn this computational with graphics processing units, then it even gets more interesting. What this exercise asks you is to look into the literature, and most likely you may find it in signal processing literature, where there is some attention for medical images. So you can think of a brain scan. So most of our heads are round, so brains are kind of round, and it makes sense to scan, and the way this might actually be done might actually be by a scan which is not rectangular, but which is more polar like. So where the scan is not, so the signals that are coming in are actually distances from a certain center. So check how the fast Fourier is applied there. Are there specific fast Fourier transforms that will actually do this? Instead of the so you can think of, if the FFT is defined for a square image, you can transfer pixel by pixel every scanned point. You can compute a point in the matrix, but that will then be again a quadratic cost. So how can you feed that more directly into a fast Fourier transform? Is there a polar version of the fast Fourier transform? That's essentially where this exercise boils down to. Okay, here is the point. So this is a lecture on applications of the fast Fourier transform. So we will not do the matrix multiplication and not do the inverse. We will do everything with component-wise multiplications and component-wise divisions. So before we do the component-wise multiplication, we do the fast Fourier transform, both on the input and the output. So what needs to be kept secret here is the matrix of the Fourier transform. So the B hat needs to be known both in the encoding and the decoding. So here it may still make sense to have a blurred matrix that, or you can think of a very simple fast Fourier transform. So the blurred matrix itself might be complicated, but the you could think of recipes that allow you to avoid to store an entire matrix. But the main point here is that the encoding and the decoding happens in quasi-linear time. So the encoding involves a fast Fourier transform, two fast Fourier transforms, but most likely you have stored the fast Fourier transform of the blurring matrix. So one fast Fourier transform then, and a component-wise product. Now I see that this is also n square, so because you have to run anyway over all the pixels. Then we do the sending, which is a linear operation, and we have the component-wise division followed by the inverse Fourier transform. The n log n here of the Fourier transforms will be on the entire size of the image. So that could be another project. How do the two, or another investigation exercise, how does the two-dimensional fast Fourier transform actually now work? Fortunately, we do not need to care about this because we are using here the FFTW package. What I want to say here is how the blurring works if you multiply with a matrix. So this is another example on how to compute. And if you want to see something, you have to be careful that the intensities have to be between 0 and 1. Otherwise, the saving of the image as an RGB type of matrix doesn't really work. But see, you get something that's kind of messed up. All right, the other glitch is that the blur matrix, we set it up as a multiplication. So here, what I did, I extended the blur matrix with ones on the diagonal, zeros of the diagonal. So this is this extension that is done here. And then I said we don't need to worry about the two-dimensional fast Fourier transform because it's the same command as the one-dimensional Fourier transform. So we do the fast Fourier transform of the blur matrix, or the BB, the extended matrix. We do the fast Fourier transform of the matrix, so the floating point matrix of our grayscale image. And then we do the component-wise product to compute the message that is now the blurred image that is safe for transmission. Okay, so two FFT calls here and one component-wise product. So one can, if one takes the entire size of the matrix, so this is quadratic in one dimension, but it is linear or quasi-linear in the size of the input. So if you have large images or a very fine scale, fine grain scale, then you will see the time go up linearly, almost linearly, with the change in size. Okay, then at the receiving end, we receive the fast Fourier transform of the blurred image. So I probably should have had now the picture in between. So what we do the component-wise division. We divide by the Fourier transforms of the blur matrix. So this is done in a double loop here, indicating that this is done with complex arithmetic. So here I have initialized the matrix first as a matrix by zeros, but if you leave off then the second instruction, it will not work because the division operator will actually complain, or the division operator will work, but the storing will not work well. So I decided to declare a matrix of complex numbers. The last step is then that we need to, in the application of the inverse FFT, we need to make sure that the we show the real parts. Okay, so I noticed that I'm at the end of my slides, and I have actually not gone through the most recent version of my slides, so in a hurry to get this done. So let me briefly, for the remainder of this lecture, flash up the last two slides. So here we go. It's almost as messy as a live presentation. So we ended here with the blurring. So what have we done? So we have presented two applications of the fast Fourier transform, and we ended chapter 4 in the textbook that I'm following. So the blurring of images is I got the idea from the textbook. That's a kind of an interesting introduction computationally also to the two-dimensional fast Fourier. If you want to know more about the discrete Fourier transform, or from a different perspective, you can also still check the textbook for numerical analysis. And I wanted to end with is a summary of what we have done uh, in the last 6 lectures. So I once said that this is also math for industry. What we try to do in this last lecture mostly, and actually also in the previous lectures, we try to get to a computational overview of signal processing and filter design. So we did this in 6 lectures. Here it goes then, the summary in 6 sentences. So the Z-transform of a sequence shows what are the important factors in the sequence, whether there's growth or whether there is decay. So the Z-transform of the impulse response of a linear time invariant and causal filter then gave rise to the definition of a transfer function. So the transfer function then evaluated at a complex number, the complex number that encodes the frequency and the sampling rate, gives us then an impression of what the filter does, what is the gain and what is the phase shift, shown in the Bode plots. So that was what we did with the first week, ending at a conceptual way to design filters via interpolation. Interpolation is one of the main properties also of the discrete Fourier transform, the discrete Fourier transform which turns convolutions into componentwise products. So that's the picture still behind me. The fast Fourier transform turns this picture into a quasi-linear operation. So an operation that works extremely conveniently fast for online filtering, as we introduced in this lecture. So we can remove low amplitude noise. We can also remove unwanted filters. And the FFT is also interesting to blur and deblur images in the safe transmission of two-dimensional pictures. So this concludes, in essence, a very important part of this course. So the last 2 lectures combined with the first 2 weeks, starting with statistical reasoning, and then in the second week on project, on technical writing, oral presentations, topics for projects, and the analyzing of data. So we are now 4 weeks in this class, so we have seen about close to 1/3 of the materials that will be covered. So we will come back to the frequency domain approach at a later stage in this course.